Hello everyone, welcome to JCE Connect. This is Professor Vinayakratan from Department of Mechanical Engineering, Jain College of Engineering, Belagavi. In today's lecture, we'll be dealing with Module 2, trusses. Let's start with trusses. Okay. So we'll see what is a truss element. To see what is a truss element, we'll consider two different coordinate systems in FEA. One is global coordinate systems X and Y. The other one is local coordinate systems. Let me consider a truss element with nodes 1 and 2 and the length of element B, LE. Now, so X dash indicates the local coordinate systems, X and Y indicate a global coordinate system. Now, after the application of force, okay, along the X dash, okay, X dash direction, truss element will act as a bar element. It is similar to the bar element, okay. That is, each node of a truss element will have 1 degree of freedom per node. So it will deform only in x dash direction. If we consider it with respect to global coordinate system, so truss element will have 2 degrees of freedom per node. That is, per node will displace in x as well as y direction. Displacement of each node in x and y direction. Let's now move on to the derivation of stiffness matrix of truss element. Let's again consider the global coordinates truss element with nodes. Then, so this is the initial position. X dash is the local coordinate systems. X and Y are the global coordinate system. Now, when you apply the force, your truss element will move from its initial position to a new position after the application of load. Now you can see after the application of load with respect to x dash direction. So node 1 will displace by a distance q1 dash and node 2 will displace by a distance q2 dash. So q1 dash or q2 dash are displacements of node 1 and 2, okay, respectively with respect to x dash direction, that is locally. Now if you consider it with respect to the global coordinate systems x and y, each node will have 2 degrees of freedom, okay. That is, node 1 will displace by distance q1 dash in x direction and q2 dash in y direction. Okay. In the similar fashion, node 2 will displace by q3 in x direction and q4 in y direction. So q1, q2, q3 and q4 are displacements of node 1 and 2 in x and y direction. Okay. So let me draw two lines, okay, which form two right angle triangles. One is a smaller one, other one is larger one. Let me take this as A and this as B. In the similar fashion, we'll do it for node 2 as well. And this let be the angle theta. So in the similar fashion, we'll do it for node 2 as well. Let this be C and this be D and this be angle theta. So displacement, element displacement locally. So Q dash is the element displacement locally. So with respect to local displacement, Q1 dash and Q2 dash are the displacements of node 1 and node 2 respectively. Similarly, element displacement globally denoted by Q. So, so it is given by Q1, Q2, Q3 and Q4. In matrix form it has been written. Now let's see what is Q1 dash. Q1 dash is nothing but A plus B from the figure. Similarly, Q2 dash is nothing but C plus D. Now our main aim is to determine the displacements q1 dash q2 dash in terms of global displacement q1 q2 q3 and q4. Let's see what will be A using those triangles A and B. So what is cos theta with respect to the larger triangle in the with respect to node 1? So cos theta is given by adjacent upon hypotenuse. What is adjacent? A divided by q1. So what is the value of A then? Q1 cos theta. Similarly, we'll do it for B using the smaller right angle triangle. So sin theta is what? Opposite by hypotenuse. So what is the opposite? B by Q2. So what will be B? Q2 sin theta. So we have written displacement Q1 dash, okay, in terms of global displacements Q1 and Q2. In a similar fashion, we can write it for Q2 dash as well. So which will be given by Q3 cos theta plus Q4 sin theta. Okay. Let this be equation 1. Now let's take write cos theta as equal to L and sin theta equal to M, where this L and M indicate direction cosines of a truss element. So rewriting the equation 1, we will get Q1 dash equal to Q1L plus Q2M, Q2 dash equal to Q3L plus Q4M. Okay. So let's write this equation 2 in matrix form. Okay. In matrix form, we'll write it like this: Q1 dash Q2 dash equal to LM00 LM, then Q1, Q2, Q3, and Q4. You can see in the first equation you don't have any thing related to Q3 and Q4. So the values in the first row in the matrix are 0 0. In the similar fashion, in the next equation there is no Q1 Q2. So the first two elements in the second row are 0. When you multiply, you are supposed to get back equation 2. Well, at what is Q1 dash Q2 dash? We already discussed in the last slide. That is nothing but Q dash. Let's take this matrix LM0000LM as denoted by L, and this Q1 Q2 Q3 Q4R is denoted by Q. So where this matrix LM0000LM is nothing but transformation matrix. So what we are doing here is your displacements, which are local displacements Q1 dash Q2 dash, are being converted to global coordinate system, okay, using this matrix L. So hence L is called as transformation matrix. It transforms displacement from local coordinate system to global coordinate system. Okay. So this is nothing but your transformation matrix. Let this be equation 4. Now, so truss element will be equivalent to 1D bar when it is viewed in the local coordinate systems. When if it deforms with respect to local coordinate systems x dash, it is nothing but your 1D bar only. So what is the stiffness matrix for 1D bar? Let us denote it by K dash, and it is given by AE by LE 1 minus 1 minus 1 1. If you consider only with respect to local coordinate system x dash, but globally it will be different. Now let's see what is the strain energy for truss element in local coordinate system. So what is strain energy generally given by U equal to half kx square, but here we'll be writing the kx square in terms of matrix form. So from the property of matrix, we cannot write um, the equation of half kx square, okay, because it's very difficult to multiply the matrices. So we'll rearrange them. Okay. We'll use the matrix property matrix multiplication property. So we can write it as, so where x is nothing but q dash, that is local displacement. Okay. So we can write the strain energy as U equal to half q dash transpose k dash into q. Okay. Let this be equation 6. Okay. Let's substitute this equation 3 in equation 6. So what will we get? So we substitute equation 3 in equation 6. So half q transpose L transpose k dash L and Q. Okay. So when you substitute the value of Q dash in Q dash transpose, okay, so we'll get here L transpose L into Q and its transpose. Okay. Let me tell you one more property of a matrix. A into B. If A and B are two matrices, its transpose will be always equal to B transpose into A transpose. Multiplication of A into B and its transpose will be always equal to B transpose into A transpose. The same thing is applied over here. Okay. Now let me again write strain energy in terms of global coordinate systems. Okay. So which will be given by U equal to half Q transpose K into Q. It is written similar to that of equation 6, but instead of Q dash it is Q. We know that Q is the element displacement globally. Now if we compare the equation 7 and 8, okay, what is the value of K? So K is given by L transpose, K dash and C. You can see it has been highlighted in different color. Okay, so this K is nothing but stiffness matrix of truss element. Let's substitute L transpose, K dash and L in this equation and find out what is the stiffness matrix of truss element. Okay. So what is L? LM0000LM. If its transpose will be, it's a column matrix. So you can see. So L transpose is this one, LM0000LM. Then K dash is given by this, and L is this. First, let me multiply the first two matrices. Okay. So this how we'll multiply. After multiplication, we'll get the equation as K equal to AE by LE, L M minus L minus M minus L minus M LM, and into transformation matrix. If we multiply these two matrices, we'll get this expression. Okay, so this is the stiffness matrix of truss element which we'll be using in the problems. Okay, as we have used for 1D bar, which is given by AE by LE, 1 minus 1 minus 1 1. So in the same fashion, we'll be solving the problems on trusses by using this equation. Okay, that is E by LE, L square LM LM N square, and the same thing has been repeated. So this is the final equation, stiffness matrix of truss element.